everyone, in this section we're going to talk about torque. So torque is the rotational equivalent of force, and it's a quantity that represents the ability of a force to cause a rotation of an object. So let's look at how to calculate it. The symbol for torque is Greek letter tau, and it's measured in Newton meters. So you might remember that this is the same as a joule. It is, but we don't say joules if it's for torque, since joules is a quantity that represents energy. Okay, to find torque, we take the cross product of r cross f. R is a position vector that points from the pivot point, so an object that's rotating will always have a pivot point through the line of the axis of rotation, and R points from that point to the point of action for each force. So it would point all along here in a straight line until the location where that force acts. And we'll look at a few different ways of thinking about this equation next. I'm just going over the basic definition for now. Okay, then F is the force vector. So to find the magnitude, since it's a cross product, we can take torque equals RF sine theta. R is the magnitude of the position vector in meters. F is the force in newtons, and then we have sine of theta, where theta is the angle between R and F. So this is a vector, that gives us the magnitude. How we find the direction is defined in the same way as angular acceleration. First of all, this is a cross product, and we know that for a cross product, it always produces a third vector that's perpendicular to the original two vectors, so perpendicular to R and F. And the direction is, if the force would rotate the object counterclockwise, like F1 here, it would pull that object counterclockwise, then that's a positive torque. Whereas if it would cause a clockwise rotation, like F2, that would be a negative torque. So from this expression, we can see that the largest torques happen when F is perpendicular to R, like F1. So that would be the largest orientation for the torque at the end of the object, so R is the greatest, and at the highest angle of theta equals 90. Any torque, other torques can be smaller. It of course depends on the magnitude of the force as well. And one interesting case is what I've drawn here for F3, where that torque is applied, where the force is applied parallel or anti-parallel to that R vector. So if it's through this line of the force, which is our straight line distance from the pivot to that action of the force, so that theta is 0 or 180, we get 0 for torque. So any parallel or anti-parallel forces will not cause a torque on the object. All right, let's look into the three methods for calculating torque. Okay, so I'm just going to take a bit of time to go through the three different ways to think about calculating torque. The first method is basically what I've described already, where we use the angle between R and F. So in this case, draw your straight line distance from the pivot point, or picture it, to the point of action of the force, and then torque is RF sine theta, and we get the sign from using counterclockwise or clockwise rotation. So the angle here, we can use theta or phi here. So it can be this acute angle between R and F, or the obtuse angle on the other side. And the reason is that sine of theta will equal sine of phi, or sine of 180 degrees minus theta. So sometimes one of them will be easier to see than the other, but you could always use either one. All right, let's look at the next method. Okay, so the second method is called the lever arm approach, which is often useful for irregular shaped objects. So to understand this, the line of action is a line drawn that's infinitely long through the force. So it's through that point where the force is acting and in the same direction. So I've just extended this line here. It could go on longer, and we could also draw it above the force. It can go in both directions. And then the lever arm, L, is a line that's going to be drawn from the pivot point, or from the axis of rotation, to that line of action, and it will intersect it perpendicularly, so at a 90-degree angle here. So I've drawn that at 90. And if you use this method, then that lever arm L is actually R sine theta. So we're really using the same formula for torque. But if you can calculate L or measure it, then we have torque equals plus or minus LF with the same sign convention that we've been using so far. Okay, one more method. Okay, so the last method is the tangential component of the force approach. This method works because it is only that tangential component of the force that causes torque. We know that any parallel forces do not cause a torque, and similarly, any parallel components of the force aren't causing the rotation. It's the perpendicular component. So what we can do is break up that force into its radial, which will be along that R line from the pivot point, that component, and then the tangential component. And the tangential component would be R sine theta, so it's just, again, using the same equation, but in another form, another geometric method here. So F tangential is R sine theta, and in this way we get torque equals plus or minus RF, so that, again, using the sign convention of positive is counterclockwise and negative is clockwise. Okay, let's apply this to some examples. When two or more torques act on an object, we can calculate a net torque. Calculate the torque due to the two forces and the net torque using each of the approaches demonstrated in class. Okay, so I've drawn this beam on the board, and let's look at calculating the torque due to each force and the net torque. If we want to calculate the net torque acting on an object, then we're going to add up the torques from each individual force. So our net torque will be the sum of all the individual torques. Okay, so I started over here with the torque due to F1. Using the first method, which is the angle between R and F approach, we have T1 equals R1 F1 sine 90. So 5 meters times 8 newtons sine 90, which gives 40 newton meters. So for R, I'm using the straight line distance from the pivot to the force, which is along the beam in this case. So it's quite simple. And then we need to decide on the direction. So this force, it would pull the beam around clockwise, so that's a negative rotation, so we have negative 40 newton meters. And then if we look at torque 2, we can see that torque 2 is the other way. It would cause it to rotate this way, which is counterclockwise, so that's a positive torque. And then we have R2 F2 sine 30, so 30 the angle between R and F. And then we can just plug in the values, 2 meters, 12 newtons times sine 30, which gives 12 newton meters. And adding those up, we get a net torque of negative 28 newton meters. Okay, so we're asked then to use each other approach, and I'm just going to show you them on the diagram because the math ends up looking exactly the same, which is why they are all equivalent. But if we want to do the lever arm approach, we're going to draw a lever arm from our force. So what I would do is, if needed, extend your force. I'll start with F2. Extend it to draw the line of action. Here mine's long enough, I think, maybe a little bit longer. There we go. And then my lever arm is here so that it intersects that line of action of the force at 90 degrees. So this lever arm here, it's opposite to the angle, so it would be this R value, R2, sine 30. And then for the lever arm approach, we would actually write it as, just get rid of this, and then I would write the torque equals LF. But L is R sine 30, so it's this sine 30, and that's F. So that's how we end up with the same result. Sometimes this is more useful, and we'll see some examples later where it is. Okay, and then if we did the lever arm approach for this torque here, again we end up with the same thing. This time for a perpendicular force, the lever arm is the same as R, because when we draw the straight line that intersects the force perpendicularly, it's right along R anyway, so nothing would actually change with how we think about that method for torque 1. All right, the last method that we want to do is to use the tangential component of the force method. So again, for torque 1, this really doesn't change anything because that's already a tangential force to the rotation. It's perpendicular already. So it would still look like that. But if we look at this force here, essentially now what we're doing instead is that we're going to use torque equals RF, and it's the tangential component of the force. So if I now draw in, instead of the lever arm, the tangential component of the force, I'll draw it here so you can see that it's opposite to the 30. It's this perpendicular component to the force here, which is F sine 30. So now it's this part, which is the tangential component. And so we would end up with the same result. It still acts at the point of action of the force, so if it's more clear to you to draw it in on this side, you can draw it there as well, and we end up with the same thing. And adding up the torques, of course, in any of those methods, we get negative 28 Newton meters for the rotation of this beam. Okay, I just checked in for the next example. We'll use the actual cross product definition. So I wanted to remind you that torque is a cross product as well. So we can always cross vectors using the determinant method if we're given component unit vector form. So if we are, then we can do this for our torque, and we'll end up with a vector with a direction. And that direction still corresponds, positive would mean counterclockwise rotation, negative would mean clockwise. And since it's a cross product, we've been finding the direction of vectors through the cross product in this course using the right-hand rule, and we can still do that here. So just like we did for the force on a moving charge in a magnetic field, we'll place our fingers in the direction of the first vector, which is r, and turn them into or curl them towards the second, which is f. So I'll just show you that with our example from the last question, and then we'll do the last example here. So what I would do is place my fingers in the direction of r, so from the pivot towards the force, and then I want to curl them in the direction of the force. So in this case, that's up for this force. So then I get out of the page here for the rotation from F2, and out of the page would be positive, so we get a positive counterclockwise rotation. Then for F1, I place my fingers in the direction of r, curl them towards F, which is down. In this case, I get into the page, which is negative for that clockwise rotation. Okay, now on to the last example. One force acting on a machine part is F equals negative 5 newtons I hat plus 4 newtons J hat. The vector from the origin to the point of application of the force is R equals negative 0.45 meters I hat plus 0.150 meters J hat. In a sketch, show F, R in the origin, use the right-hand rule to determine the direction of the torque vector, and calculate the torque vector. Okay, so I've sketched the vectors here, so we can sketch those like we would any vector. For the force, I've drawn them here, so negative 5 newtons to the left, and then up 4 newtons. And then for R, that's negative 0.45 and up 0.15. It's clearly not to scale, but they're not the same units anyway, so it doesn't really matter how long the lengths are. It's just the direction is helpful for giving us the right-hand rule. Okay, so, and that's next. Let's use the right-hand rule to find the direction. So if that is y and x, and this is the negative x-axis over here, we're going to place our fingers in the direction of r, like that, and then I'm going to curl them towards f, so I'm curling mine that way, and my thumb is into the page, and that's in the negative k hat direction, so that's a negative rotation, clockwise rotation, again like this. So curling r into f. Okay, and then looking at our vector, I've set this up. So we want to do the cross product. We put the first vector r and its components here, I hat, j hat, k hat in the first line, and then the force components below. And then looking at this, so that you can use any determinant method, or you have the long equation if you want to use it that way. But if we were to cover up the first row in the first column, we'll get 0 times 0. In the middle column, again, 0 times 0. So the only component that will be non-zero is the k hat. And we know that because we also know that it is a cross product, so it's going to produce a third vector that's perpendicular to both the original two, which are in this xy plane. Okay, so then we can cover up this k hat component and do the determinant. The method that I do is to cover that. Would be positive, negative, positive for this k hat, so it's positive. And then I'm going to multiply these two minus this diagonal here. So negative 0.45 times 4 minus negative 5 times 0.15, which gives negative 1.05 Newton meters k hat for the torque, which we would expect already from the right-hand rule. So our cross product also gives us the direction. We don't need both, but it's a good idea to confirm. Okay, we'll look at how this relates to angular acceleration in the next section.